Let's get us started here, and I did make a comment last time and want to follow through because there was no real good consensus here, but it gave me a chance to think about this in much more detail and have real grave concerns here. Here's where we are today. Here's kind of the plan. In a minute here we will change and go from the electricity to the magnetism, the second half of this chapter. And so we're going to try and then cover here chapter 29 and then into chapter 30. Now the timing on the schedule has us then taking the test right there, and that's fine, but I really don't think it's a good idea, and so I have it there. I want you guys really to decide if it's a good idea for you, but I circled it, and I circled it in red because what you don't know and what you're going to see is in chapter 30 you're going to see some really hard stuff right here on 2 days before the exam. And I really don't think it's a good idea to give the exam that next one. And so I really think we should go into that next week for sure. I know for some of you, as you were telling me, you have math tests there, and that's, I know, a problem also, but I don't think it's as big as a problem of going to a test that you don't know the material. So it's better to have a time for that to sink in, even if you have tests on 2 days here. So with that in mind, I thought I would take a vote giving these options here on when do you guys want to do the exam. And we could, like I said, we could still have it here. My advice is that is a terrible idea because it is just going to be too much material to try to get in 2 days. But you know, I can give the test. I mean, it's no sweat off my back. I'll know the material, but I don't feel comfortable with it all. That's why I brought up the whole idea of moving the test, not you guys. I know sometimes I have students coming to me and saying, oh, this is a bad day for a test. We have other tests, and then we kind of have a discussion and a movement. But this time it's me initiating it, saying the 31st is just going to come too tight with some hard material. And I'd rather start going into the next chapter, where actually the next chapter, what you don't know is we use the chapter 30. So as we go into the next chapter, even though we're learning new material, you'll see that will really help you with the old material because it builds on itself. And when we get into this chapter 31, I keep saying, okay, remember what we learned in 30. So even though we're in 31, we're also kind of reviewing 30. And because of that, I'm really thinking this next week, even if you guys have tests on the same day or close to the same time, if you study over the week, and I think it's well worth it. All right, so with that, I'm going to ask for a show of hands. I'll just go in chronological order here, starting on the 31st. Who thinks we should leave the test where it is on the 31st? Raise your hand. Oh, good. Nobody. I like that. All right, because I do. And I was talking with Don, and Don said the same thing. He goes, man, you give them the test on the 31st, and they're just going to bomb it. All right. So I agree. All right. So how about the 5th? Who? Raise it high so I can count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20. So good. Now I'll put 20. How about the 7th? Oh, a lot of people like the 7th here. Wait. Oh. You coming in? Are you voting here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, no, 20, 21, 22, 23. You try to get me to count you twice. 20. 23. Now, okay. So it looks like the 7th is a better date, and so I think we'll go with that. I wanted to point out, I should have said that Don already told me that regardless of whether it's the 5th or the 7th, since we're going to be done with the material, he'll schedule a review on the Sunday. I think some of you had commented that if the test was here, the review would be on a the Tuesday, and that would be hard. But Don was saying no, he'll still do it here on the Sunday, so we will still have that met. All right. So.
How does that affect the third exam? Isn't that going to shorten the time back and the third exam?
And the what?
The third exam?
Well, the third exam, obviously down here somewhere, okay, can't be changed at all. It's the last scheduled day of instruction.
Yeah, what is that?
Well, okay, you might say then there's less time between the second and the third, which is why we're going to be doing chapter 31 here, so that we're not trying to cram material in. So we don't have to cram the material in any faster. All we're doing is honing it so you can, give some of these hard integrals we're going to do a week to think about before we have the test. That's the point. Yeah.
Chapter 30 like the most difficult material we're going to cover as far as the next week test.
Yeah. Yeah, it probably is. I put 30 in that same category as chapters 23 and 24 put together. Because your author is trying to teach you, as you'll see, there's a good analogy between electric fields and magnetic fields. And in 23, we did Coulomb's law. Well, we see an analogy of that. Chapter 24, we did Gauss's law. We see an analogy of that. But your author says, oh, since you already know those, we'll put them in one chapter. So those were hard chapters, if you remember. And then he puts them together. Now, the good news is they are by analogy. So you hopefully will have a little easier time with them the second time through. But magnetism does tend to be a little bit harder, and even though he puts them together, so between being a little harder and putting them together, it's a tough chapter that, like I said, I really don't want to see you guys go with 2 days from some of the hardest stuff to boom, and then the test, yeah.
So what's the final decision?
So the 7th, sorry. So the 7th wins, okay, but barely. I wish it wasn't quite so evenly split there, but maybe by throwing this out there for those of you that unfortunately may end up with 2 tests that day, use that extra time ahead wisely. It's spread out here now, and I think you will appreciate, those of you who end up with 2 tests on this day, really appreciate rather than having 2 tests here and have that extra time, although you might have preferred that one over the other one versus that still give you the extra time. All right, good. So it wasn't an ideal choice, but we'll go with that, and hopefully that will work out for the better of everybody involved. All right, well, let's go into magnetism now. And so as I kind of already started to say, as we started our little discussion here, we are halfway through class now. We have done half of the material. We have done 6 chapters, and we have done electric field. And as you know, the title of this class is Electric and Magnetic Fields. Electricity and magnetism. So half done. We've done electricity. And let's go back and look at what we have done. We started by looking at conceptually the forces. We did electrostatics. You might remember me standing up here on the first day rubbing vinyl and acetate and looking at the forces and just getting into the idea that there are charges, that there are forces, that there are fields. And it was very conceptual. And that's exactly where we're about to start. And so hopefully what you will see today, as well as the whole rest of this semester, is everything we did for electricity, we're about to repeat for magnetism. There is a good correlation from one to another. Now, there are things that are different, and unfortunately, magnetism is different enough that it does get kind of complicated in terms of their calculations. But like Coulomb's law, you will see something very similar. Like Gauss's law, you will see something very similar. Like electric fields, you will see magnetic fields. Like electric forces, you will see magnetic forces. I think you get the point. And we will spend then, like we did for electricity, 3 chapters learning the basic physics, and then 3 chapters applying magnetism to our electrical world around us. And that's what we just did. We did 3 chapters on the physics, and then 3 chapters, we did capacitors, then we did Ohm's law, then we did Kirchhoff's laws. And so we applied these whole ideas. So that's exactly what we're going to do now here. So to get us started, I thought I would take a magnet, a compass, if you will. I'm a little concerned that you may not be able to quite see this when I hold it this way. Maybe if I tilted it a little bit. But can you guys see how this needle, which I'm about to call a compass, can spin? And if I place it here on the edge of my desk, and again, maybe just tilt it a little bit. I really want it more level than that, but so that you might be able to see it better. It will, maybe tilt it back a little bit. There we go. But one end of this will end up pointing to the north, which of course means the other end points to the south. And so our first piece of this magnetism is to get some vocabularies. And just like we had electricity, where we would say you have a positive and negative charges, when we get into our magnets, and in this case, we'll start with just a simple compass, because that's where the vocabulary starts, and that's where I want to start here today, is that if I take a magnet, and my first magnet being a compass, kind of the first discovery of magnetism, is that all magnets have then 2 different sides, or what we call poles. And so if I take a compass, or I take any magnet, one side is going to point towards the north and the other towards the south. Now watch. Let me get rid of this one for just a moment and place it over here. Let me take another magnet. And maybe I'll even pick up a couple of nails here to show you. Yes, it is a magnet. But let me do the same thing here. Let me take and put this magnet in what I'll refer to as a boat. Okay? And the reason the boat is here is because the way it sits without any water in it, there is lots of friction between the boat and the bottom of the lake, if you will. But if we put a little water in our lake, eventually the boat will float. When it floats, it'll have little to no friction. And so if there's any kind of interaction, something will happen. And again, without explaining the physics of how or why it happens, of course that's what the next 3 chapters are all about. Clearly, something happens. And if you guys can see, and I tried to get a clear pan so you can look through here, but I think you will notice that one end ends up pointing towards the north, the other end towards the south. And then so step 1 here is just terminology, the vernacular here, okay? And so I have what I would call a north and a south pole. I have one end that heads towards the north and one end that heads towards the south. So maybe I will call this side 1 is what we would call a north pole. Maybe a little more complete, I should call it a north seeking pole. Because when I say North Pole, I clearly do not mean what we would call the geographical North Pole. This side right here, we are going to refer to, and I'll put a little black dot on it, we are going to refer to it as the North Seeking Pole. It is not where Santa Claus lives, the geographical North Pole, okay? And that obviously is an important difference. As well as the other side, we will call it a South Pole. But what we really mean by that is it is pointing towards the south. It is south seeking. It is not really at the South Pole, which penguins live in the South Pole here. So we don't mean where the penguins live, we mean it points to where the penguins live, okay? And so that's our terminology. And so keep that in mind, because we often do say north. Also keep in mind that notice I did not say it was positively charged. See, charges are reserved for electric fields. Magnetic fields are something in addition to that. Now, I want to emphasize that because as you will see today and for the next 3 weeks, when I try to teach you about magnetism, a lot of what I'm going to teach is also going to say, well, remember what we did for electric fields? It's just like electric fields. And because they are so close in their similarity, it's very easy for the beginning student to say, oh, my magnet is positively charged. My magnet is negatively charged. No, right there you're just mixing up the concepts of electric fields and magnetic fields. Charges are the sources that create our electric field. Okay? What I'm trying to show you is something yet in addition to. And as you'll see, especially as we get to the end of this class, you could have electric and magnetic at the same time. And some of the best technology we will learn about and experiments we will do and problems we will solve are when we have both electric and magnetic fields happening at the same time. So that's coming up towards the end here. But it's my way at the beginning to say, please keep in mind that what we're doing now is magnetic fields, and it is in addition to an electric field. You could have an electric field also, but you may not. And so hence our wording is very different. These are poles. Okay? Now, let me take one step further here. What if I were to break the magnet in half? Do I get two separated poles? No, I would not. And here is one thing that is significantly different and is going to make everything else, unfortunately, slightly different between magnetism and electricity here, is that when you break a magnet in half or when you separate it, you don't get two separate poles. You don't get what we'll call maybe a monopole. You still will have a dipole. You will still have two different poles, a north pole and a south pole. Now, of course, I haven't really given you any information why, other than this is, what has been observed. And I showed you very little here so far of what has been observed. But I did try to point out all magnets then have two poles. And when you break it into half, this side becomes a south and that side becomes a north. And so maybe I should add to this, there is no such thing as a monopole. And if this was electrical material and I had positive charge and negative charge and broke it in half, then I would have this object just positively charged and this object just negatively charged. And so that doesn't happen with magnetism. So in that sense, magnetism is different than electricity. Yeah.
What if it's spherical? What if the magnet is spherical?
Well, if the and actually we have some in there what you guys are going to play with in lab, but if I took a material that was a sphere and made it a magnet, okay, the magnetic field is not spherical. The material is spherical. And what would happen is I would get a ball like this that I might say here's north and here's south. If I split that ball in half so that I had two hemispheres, okay, what ends up happening is this becomes a north and that becomes a south and that becomes a Well, that stays a south, and that becomes a north. And I still end up with no monopoles. Okay? Now, don't get me wrong. I say there's no monopoles because we've been looking for monopoles for hundreds of years, and maybe we just haven't found them. In fact, there are many scientists who speculate that nature really meant for magnetism to be exactly similar to electricity, and we just haven't figured out a way to separate them yet, and they really could be. I'm not one who subscribes to that for a number of reasons, but we have looked and we have looked, and there's some really neat and fascinating and expensive experiments that have gone on in this world. Billions of dollars have been spent and nothing has been found. And so we, at this point, just say, no, nature is not that way. It kind of seems like it would be, because there's a lot of things in nature that we have gotten by saying, well, this was similar to that, therefore we're missing this piece, let's go look for it, and we find it. And we've done that for magnetism, but no luck. Yeah.
So what if instead of a ball, what if you actually have all the south pointing things going to the inside of the ball and have all the north pointing outside? It would be like a pseudo monopole of some sort, wouldn't it? Like, for example, you have all the magnetism points in, like you have a whole bunch of different millions of different magnets. You can have them, all the south points in the center of the ball and have all the north points outside of the ball.
Oh, okay. I guess you're saying this. If I took a bunch of south, is this kind of what you're saying?
Yeah, kind of.
Okay. I guess I would say that then in this area, kind of in here, I have what you called a pseudo monopole. Okay, fair enough. And I'll do you one better. This is exactly what we are going to do in lab. We are going to try to make a monopole. We are going to take some magnets, and we are going to do, not quite like this. Here's what we'll do in lab. We will try to measure the field from a monopole. Since they don't exist, it's kind of impossible. So what we will do is we will take a magnet. And we will make a magnet really long. And we will have you measure the field close to that one, with the idea that you are so far from that one that we have something very, very close to a monopole. And so if you looked ahead in the lab, you will see that next week's lab is measuring the magnetic field from a monopole, and yet they don't exist. It doesn't say monopole. It says the 1 over r squared value. And if you remember, for electricity, that was the first experiment you did for electricity. You did a measurement of the electric field as you moved further away to show that the electric field decreased as a 1 over r squared value. You will do the same thing in lab. You will measure the magnetic field as you move away from one side of the magnet and show that the magnetic field decreases with the same numerical value, a 1 over r squared value.
Is it possible to force a monopole?
To what?
Force or induce a monopole?
No. Never been found. But, like I said, hasn't stopped people from thinking that there is, hasn't stopped them from experimenting, and, you know, it would be a major discovery. It could be your Nobel Prize. I mean, it would really shake up the world of science as we know it today, because we've speculated for years and years that they have them, and we've kind of just decided that they don't. That's one thing nature has decided not to give us symmetry. And like I said, there's some good arguments that I subscribe to that says, no, nature doesn't have them for good reasons. Oh, yeah.
Isn't magnetism just a pseudo force of the electric field? The electric force?
I'll say yes and no more. How's that? Till a couple more weeks. Yeah.
If you took two magnets and you glued their same poles together, do they cancel out, or do they become like one magnet? Glued and moved the north and north together. Do they like
Right, so then they would cancel out, and that's kind of the reverse of what I have here, exactly. So if you were asking, what if I put these together? What you're going to get then is when you crunch them together, becomes the North Pole, this over here becomes the South Pole, the north and the south kind of blend together and cancel each other off. Right, right.
You
Exactly.
have like two north or blue together.
Ah. Well, I'm glad you asked because I'm about to do that for you. Right, right. Okay, but let me just do that one first and say, okay, this is step one, if you will. And step one being, oh, I didn't get my rag wet. Oh, hang on. Yeah, maybe this dry one will work enough. Yeah. Yeah, that's gonna make a mess before the end. All right, but step two, and leading to your question then, is what would happen if I were to take two magnets, maybe a north, and of course I'll have to put a south over here and a south over here, and say, well, what would happen if I put two magnets close together like this? Yeah, hopefully it doesn't surprise you that if I were to take like poles and put them next to each other, what do you think would happen? Yeah, see the analogy? Didn't we do that? What happened if you brought two positive charges? They would repel. What about two negative charges? They would repel. Now in that case we would say they would repel because of the electrical force. I want to just add that what would happen here is they would repel because of the magnetic force. And so it's a different force, but it's still the same general idea. In fact, that's why, besides having this bar magnet, which I put a black dot on there to represent the North Pole, I can take another bar magnet and put it on my boat, place it at, say, 90 degrees and let it go, and wait for it to turn around to find out which side is the north-seeking pole and which side is the south-seeking pole. Okay, so this side is the north-seeking. I'll put a black dot on it. And actually, I won't even bother to take it off the boat, but I will pick this one up, and with the black dot, north, what do you think would happen if I brought a north near a north? Right? They repel. And so, sure, not a surprise, and again, you're seeing the analogy. Let me let it settle down here for a moment. Decide which way is north again. Okay, so this is the north-seeking side of that magnet. Oh, let me come back to the one in my hand. I'll take the other side. So if the black dot was the north-seeking side, this must be the south-seeking side. What do you think would happen if I brought the south near the south? Yeah, it's going to repel that one, right? And so like poles repel, just like charges repel. But here they repel because of magnetism, and in the other case it was electrical stuff.
So
Yeah.
like North Pole, the place is technically south, because the North Pole is seeking.
I'm so glad you asked that, because hopefully we'll get that far today. That's why I want to emphasize, when I call this a North Pole, it seeks the north. That means buried in the earth at the geographical North Pole must be a magnet that has its south-seeking pole. So there is a south-seeking magnetic pole in the Earth's geographical North Pole. Easy to miss that, yeah.
How do they make magnets?
I'm glad you asked that. Step 3, hang on. All right. All right, but I do want to show you the other part of this. So what do you think would happen? And this one's probably so obvious we can just move forward to your question in step 3. What happens if I take the south near the north? Right? It attracts it. What do you think would happen if I brought the north near the south? And it would attract it. And I could, if I'm clever enough, make things attract and repel and make an electromagnetic motor and a vacuum cleaner and a garbage disposal and an air conditioner. Exactly. And that's what we soon will be doing here. All right? And so here are this idea. So finishing up my picture then, I guess like this, I would have a force pushing them away. Maybe I'll even put a little sub M underneath to emphasize this is a force. This is a magnetic force, and don't confuse that with electrical force. Same thing here. These two magnets would be pushing away. They would have an F. Newton's third law says they would be equal and opposite, and they're caused magnetically. The other two options are a north and a south near each other. They too would be they too would have forces, but they would have attractional forces, and they would be magnetic. And north on this side and south on that side, doesn't surprise you that you would get, again, magnetic forces, but they would be attracted. Okay? And so we do have this whole idea of forces, just like we saw in our first chapter for electrical ones. So you can see, I think you can begin to see the analogy, and that's why your author says, all right, since these analogies are hopefully pretty straightforward, we'll cover a lot of ground in a single chapter. And so these next two chapters have really a lot of information in them, where we took 3 or 4 chapters to do back when we did the electricity. Now, I think at least in part of your question here is, where does this magnetism then come from? Right, I mean, if this was electricity, and I put on the board, where are these electric fields or these electric forces coming from? You would answer that by saying, what caused electric field? Charges, right? They could be electrons, they could be protons, but the charges are what create the electric field. And so your question, which said, where or how do you make a magnet, really boils down to what is the cause of these magnetic forces and these magnetic fields. Okay, and so point number 3 the author wants to get across is that the source of all magnetism is from, and this is going to be big here, moving. Oops, I shouldn't put in quotes. I really mean moving, but I want to emphasize it. Moving. Moving. Okay? Charges. And so you can see that the charges come into play, but the charges themselves just make an electric field. When they start to move, then they make a magnetic field. Let's see if I can illustrate that a little bit. The whole reason I brought this, I think there's some small paper clips in here. Here's a good one. And this little set of wires here is to kind of set the stage for this. We're not going to do any calculations quite yet. I mean, this first part is just understanding the vocabulary and the concept here. But this, as I think you can see, is a power supply with a bunch of wires. Okay. It is not a magnet. I could not say, hold this paper clip. Doesn't work. Now, a magnet would easily pull and attract the paper clip. And so I would say this is not a magnet. But the reason I've hooked it up to this power supply is because then, if I crank up the current, don't I have moving charges now? And if I turn off the current, it's no longer a magnet. And so this is my first step towards showing you what causes the magnetism. And your question, how do you make a magnet? And there's not just one answer to how do you make it. But going further back to what is the cause of the magnetism, I want to emphasize it's not just the charges. Charges make electric fields. moving charges make magnetic fields. So of course, if you have a moving charge, don't you have both an electric field and a magnetic field? Yeah. Now here at the beginning of our magnetism, let's not worry about the electric part of it right now, okay? That we will add later on. But the point here is just to say we do have magnetism, and magnetism comes from moving charges. Without moving charges, you don't have magnetism. And everything we're going to do for the next couple of weeks, if there's magnetism, we can somehow come back and point to moving charges. It may not be as simple as a power supply and wires. It may be a bit more complicated, like this one, and so we should talk about it, but guarantee it will boil down to moving electrical charges at some point. Did I see a question?
You're probably going to this, but what's causing the moving charges in the rod right there?
Okay, so let me build up to that, because I think nobody asked the question, well, where's the moving charges here? Well, it's a power supply, it's a voltage, it's got the resistance in the wires. I mean, we just spent 2 chapters doing Ohm's law, so I hope nobody's asking, where do the moving charges come in this one? That's not what you were asking. What you were asking is, well, wait a minute, this is obviously a magnet. Where's the moving charges in here? Well, I'll tell you what, let me do something a little bit different. Before I get to this one, let me get another piece of metal. Now this piece is not a magnet. At least it's not a magnet yet. Are there any moving charges in here?
They are moving, but they are conflicting with each other.
Exactly. And so, don't forget that if you were to draw a picture or get small on a microscopic level, and you could go down to the atomic level, and I could go down to one of these atoms of iron and say, here's the nucleus right there. And I could look at the electron in here. And to the best of my ability, let me kind of draw a sphere around the nucleus. And so here will be kind of a cross section here. Maybe I'll also do kind of a equator here. And so if you imagine these electrons that are in this shell, if you will, and maybe in orange, what's happening is maybe the electrons on this atom are going along the equator, something like that. And so as I look at those electrons, they are in a plane, a horizontal plane, and they are going around in this direction. As I look at the next atom, and again, maybe to the best of my ability, which is pretty bad, I know, I'll draw a sphere. But I would have electrons in that one too. And the electrons in that one may be in the same plane, I don't know. But let's just say they're in the same plane, but they're going in the other direction. That's moving, say, clockwise, but that is moving counterclockwise. The two together result as an equivalent of zero motion. And we could keep drawing these. We could go to the next atom and say, okay, in the next atom, maybe what we have is an electron in a vertical plane. And it's going around in a counterclockwise direction. Because the next atom might have an electron that's also in a vertical plane, but going in a clockwise direction. So what do these two atoms do, unfortunately? They tend to cancel each other out. So do I have moving charges? I would say yes, individually, but when I add them all together, the net movement is zero. And so if I just throw a bunch of random atoms out there, like was done with this bar here, and was probably done with this nail, there was no effort to make all the electrons in here move in the same orbiting plane clockwise or counterclockwise. None whatsoever. So the difference then between those pieces and these atoms is these atoms here have been deliberately twisted and set up and aligned so that as many as possible are orbiting in the same plane and in the same direction. And so, do we have moving charges in here? Yes. And because it's not hooked to a power supply, this one's a little bit harder to convince than, this one's a little harder to convince than that one. Of course, that's why I showed you this one first. But this also has moving charges. In fact, it's even more complicated than that, but that's enough for us to get started, because not only are these electrons orbiting like the Earth going around the orbit, it's also spinning. And so these electrons have motion not just from their orbit, but also from their spin. And that's a moving charge too. And that contributes and can contribute significantly to the amount of magnetism in your material.
Do all the charges have to be the same, or can you have a net charge of 0, but not a net charge, net movement, and still have magnetism?
Let me emphasize, notice that I never said that bar had a charge. It does not have a net charge. The number of electrons in that atom, it's 26. Is that what iron is? My piece of iron? Where the heck's iron? Yeah, 26. So this piece of iron, this atom right here, has 26 electrons. Of course, I've only drawn one here for simplicity. But it has 26 electrons and has 26 protons. And every atom has that. And every atom then is neutral. And whether I hold this nail, this rod, or this bar, they all have a net charge of 0. There is no electric field here. That doesn't mean it doesn't have, if I can do a double negative there, a magnetic field. Because in this case, although the net charge is 0, the atoms are all lined up so that they all orbit in the same plane. Okay, and in the same direction. So I get magnetism from this one. But of course now a magnet is a bit more complicated than just a simple piece of iron. We've got to take the iron and we've got to line up the atoms, which is getting to your question. How the heck do we get that? I'll show you, yeah.
So it's not because the bar is an ionic compound of any kind? Or?
No,
Okay.
no. It's the movement of these electrons. And unfortunately, nature doesn't really like to have them all going in the same direction. And so most of our materials are not magnetic. For those of you who've done chemistry will know, as you're filling up those shells, it likes to, you fill it up and in a certain order, and they like to go in different orbitals, different planes, different direction, different spins. And by the time you hook it all up, we don't get magnetism. So very few materials end up being magnetic when they're all said and done. And iron is one that is cheap and easily available and does become very magnetic. So I got a bunch of iron up here. Okay. So again, going to this whole idea, all magnetism does come from moving charges. Let's do this a moment. Remember this bar that did not pick up this nail? Because, or the paper clip even, which is even lighter? Because it is not a magnet? Question?
Is it more important for them to rotate the same direction, or more important to rotate the same plane for magnetic force?
Wow. I will say probably the same direction, because if they're not in the same plane, there's probably a component of the motion, that is in the plane, and so I will answer it that way. Although, since other things are going on, the Pauli exclusion principle I was mentioning in chemistry, that's far more important, and it really kind of mutes your question because of the orbitals and the Pauli exclusion principle of how they have to be put in the orbitals anyways. So, but what I wanted you to see is this for a moment. You already saw that if I turn this on, this will now become a magnet. although not really very strong. It really has troubles picking that up. Although it can, once I pick it up, it can kind of suck it in here. So it definitely is a magnet. It's just not a very strong magnet. What if I did this? What if I put this, which, remember, it's not a magnet, in here?
Electromagnetism.
And I'll just hold it in here, if I can. I'm going to hold it in there and turn this on. This is what we call soft iron. Now, soft in the sense that if I tried to bend it, I don't think I could. But soft in the sense that if I put it in a vise and hit it, I probably would bend really easy. In other words, these atoms are not locked into place. Remember, each one individually has a spin. Each one individually is a magnet. So what if I were to put this in a magnetic field? Wouldn't that twist each atom so that they're all aligning in the same direction? And then, when it comes to moving charges, I would have not only the moving charges from this power supply, but I would have all the charges of every atom going in the same direction. And so I claim that by putting this in here, I can make a magnet that, as you called it, an electromagnet. That is, I can turn it on and off, but it would be stronger than it was without here, because part of the magnetism is coming from here. And what I hopefully will convince you of, this is an amazing amount of current compared to here. I mean, you think you turn this on, I think I cranked this up to about, well, what was it? 20 amps. Sounds like a lot. Compared to the number of electrons I have in here, 20 amps is small. This is going to be like 100 times that. And so this will be 2,000 amps, or the equivalent of 2,000 amps. So, remember this paper clip?
Where's it flowing to? Where's it flowing from to?
Easily picks it up. Doesn't pick up the nail. Turn it on. Easily picks up the nail. Oh, maybe I should have turned it off. Put it in the box of nails. Doesn't pick them up. Turn it on. Picks up plenty. Turn it off. And they fall away. Okay? And so the idea is to get those atoms to align. Okay? And your question about where they come from, you're missing the point. They don't come from anywhere. They're in the atom. That's where the electrons come from.
Currents, like where does the current flow come from?
It goes from one side of the atom to the other. One side of the atom to the other. Yep. Yeah.
What about that other bar, though? You're not connecting that to any source of any kind.
What other bar?
The other bar, not the iron one.
Okay, so now, this, and the reason I was telling you this was soft iron is because once I turned on the current in here, which made a field, that field kind of twisted those atoms, but not every material will allow the atoms to turn. If it is a hard steel, which is most of the time what we want, they can't turn. So this makes terrible construction material, but great magnetic material, because the atoms did twist and lined up. And in fact, they lined up, but they really only stayed lined up because there was a field on it. What do you think is going to happen now? They don't stay lined up, because remember, these atoms are at a temperature, room temperature, and they're bouncing around. So the bouncing movement wants to break the atoms away. And so that happens in this material. But this material, this is a hard iron. They could not be simply lined up like this. and put them in here. But the good thing about it is they're already lined up. So finally getting to your question, how do I make this? It's real simple. I take some iron and I heat it until it is a liquid. I pour it into a mold like this, put it in here, and turn it on. That'll make all the atoms lined up because they can move when they're in the liquid state. They then harden, and they're stuck this way, and so they are all stuck together, and I have what I would call a permanent magnet. And so that's why we have things that we call electromagnets and things that we call permanent magnets. And my point being, all magnetism then comes from moving charges. Whether they be moving charges from an external power supply, or whether they be moving charges within the atoms, whether they be atoms that stay there or shift around, doesn't matter. All magnetism comes from moving charges. Oh, a lot of questions, yeah. In this one? Well, no, because they are bouncing around, and periodically, once in a while, a couple of things will happen. What will happen is maybe 2 or 3 will come together just right and hit it hard, like it is at a higher temperature. And it's not really at a higher temperature because temperature is the average movement, but once in a while, 3 or 4 will come together and knock one out of alignment. If I heat it up, the chances of that happening are even better. If I heated it hot enough, then it would no longer be a magnet. If I drop it on the ground, I've just lost maybe a fraction of my magnetism. Fortunately, this is really, really hard iron, and I bet it is still a magnet. But it is probably a little weaker. So if I did this a couple of thousand times, it probably would not be a magnet. If I did the reverse of what you're asking, you might be able to see it with this big magnet. Remember, and maybe I'll go to a smaller paper clip. But if I take a small paper clip and this nail, I cannot pick up that, which simply tells me that all of these atoms in here are not lined up. This very strong magnet, if I place the nail in here, wants to twist them and get them to line up like we did with this. However, these iron are pretty strong. I mean, that's why you make a nail, so it's strong. So that's strong iron. I would suspect that only a few twisted, but not many. In fact, let me help it. If I were to hit it a few times, probably each hit was enough to jar a few of them. And so maybe I have, a couple billion, which is a small number, by the way, lining up. And the more I do it, probably the more billions I have. But very little are lined up. But I'm hoping that I have enough that I can at least pick up that paper clip and convince you that it did not pick it up before, but hopefully it will now. Yay! There we go. And so I have got a few of them to line up. Yeah.
With the one that you connected to the power supply, why do we only have a magnetic field inside? Why doesn't it absorb?
Well, let me wait until the next chapter where we actually start calculating the strength of the magnetic field. And what you will see is inside is very strong compared to the outside. There is a field on the outside, but inside is much stronger. And that's why you saw this paper clip really get sucked in and be held on the inside really well, and on the outside really wasn't holding it unless I made the field really strong. Then on the inside it was enormously strong, which is why if anybody's had the unfortunate pleasure of getting an MRI, you need to put the human body in a very strong magnetic field. So they have this bed that comes out and the patient lays in and they've got to go inside, which freaks people out. And so they say this is a big problem and a challenge for people who really need an MRI, but then you lock them inside this little tube to be able to measure, to get a field strong enough for them. recent years, the MRIs have used what we're going to call Helmholtz coils, gives us more open space, and they say that makes patients feel much more comfortable and relaxed because you gotta hold still for a while inside there. Yeah.
Wait, you said that in order to produce a magnet, the atoms have to be able to rotate, right? Such as in the salt iron like that?
Yeah. They have to rotate.
So if
Or I have to get them aligned.
you said there are hard steel something like that where the atoms are anchored to the wind,
Yeah.
part of the move and twist, does it mean they are non-magnetic because you can't produce a magnetism in them?
No. No. No, I just mean that there's a bunch of atoms that at first they're in random directions. And the point is if I get them lined up, then I would have the equivalent of a net current.
But what about, but you said that the atoms have to be able to rotate so that they have to,
Yeah.
like in salt iron. But you,
Yeah.
but you said there are hard steels that have the atoms anchored. So would it mean that a magnetic field will have a harder time affecting them because they're so...
Oh, yeah.
So doesn't mean that hard steel is non-magnetic if it was
No.
non-magnetic to begin with?
No. Just a harder time, as you said. But still could. Yeah.
Like the first thing when you said you cut a magnet in half, and then it's another magnet. Like, what if you like keep going like it's one atom?
Well,
magnet?
right, and maybe now you can see our first statement that there is no monopoles, because now what we end up having is that if you had all these aligned, then let's say they're all aligned so that each atom had an electron going in a vertical plane this way. Okay? If I cut it in half, then this half of the magnet would still have a bunch of atoms going this way, and this one would still have a bunch of atoms going that way. It would just be a smaller, weaker magnet, but it would still have a north and a south pole. It just has half as many atoms. Exactly. And if I keep cutting it, eventually I will get down to one atom, and that one atom would be a magnet in itself, because it would be going there and around, and it would have a north pole and a south pole. Smaller than that, I guess you would say I no longer have a magnet, because I guess if I separated the electrons off, they're not moving anymore, except that if I did separate them off, I could hold them in my hand and they would spin. So then each little electron would be a magnet, and so I'd have 26 little magnets, each having their own north and south pole. Now, I could even take the nucleus apart, and each proton then would be spinning, and it would have a magnet. So if I take apart the proton, they get quarks, but then they're spinning too, and they make a little magnet. So far we haven't found a monopole yet. Yeah.
So essentially everything is a magnet, just they have canceling.
Yeah, that's maybe a good way of looking at it. Most of our every individual atom is actually very magnetic, but when you put them all together, they can cancel each other off, and most materials do that. And so most materials, by the time they get to be this size, we say are non-magnetic. Like a piece of copper and a piece of aluminum, we say they're non-magnetic. But if you had one atom of copper, that's not the case. Yeah.
Can gases be magnetic?
And then gases could be magnetic too, sure.
Since the Earth has a magnetic field, the north and south pole, wouldn't the concept of a monopole cause a problem, like in terms of just the Earth in some way?
No, I don't think so. No, yeah.
Is the axis of the magnetic field at a right angle to the spinning Earth?
Yeah. And that's the direction of it. But again, I'll ask you, let's wait till we get into some math before we look at the shape and the size of the magnetic fields. But obviously at this point, I'm just trying to give you the concepts here. Yeah.
If the atoms for this way, why don't we usually use plastic or use metals?
Again, not many materials ultimately end up with us allowing us to have the electrons in a plane. Our plastics, unfortunately, don't do that. Our plastics, when you start putting in a bunch of atoms that make up our plastics and the electrons, you get some going clockwise and some going counterclockwise, and even if for a moment in time you could stop the electrons and all going, say, one direction, counterclockwise, and make them all go clockwise, nature would put them back to an even balance of clockwise and counterclockwise. That's the,
It's like a hard plastic.
yeah, that's the Pauli exclusion principle. Because again, we're not twisting, I'm not saying the hard plastic, we're not twisting the atoms. The hard and soft has to do with the twisting of the atoms. That is just the pure rotational motion of the electrons. And so they could just go this way, and then, again, without getting into quantum mechanics or Pauli exclusion principle, you leave them alone, they stop and go back the other way. And so our plastics will not, at least yet, be magnetism. That would be actually a great material science problem. Yeah, magnetic plastics. That would be great. Just like a lot of people are working on conductive plastics. Yeah.
So how come the Earth has a magnetic pole and the North and South pole?
Well, the Earth, and we'll get to the Earth, but I'll just put it this way. Remember, the core is very hot and it's molten. The Earth is also spinning. A combination of those two together make moving charges within the internal of the Earth, and the moving charges make magnetism. Yeah.
Why does the electric force cause the atoms to all line up?
Magnetic force. Magnetic force. Well, again, I haven't really said much more than this so far, that if I take two north poles, they repel. So if this is my atom and it is spinning in such a way that I have a north pole pointing up for this one, and maybe this one I have a north pole pointing down, but I come along with an external magnet, north pole, that would make this magnet, this atom want to turn over this way, and it would make this one want to turn over that way, and it would want to make all the south poles go towards the north from my external one. And then that's what I mean by making them lined up. It's a magnetic effect. And I'm not even trying to answer why do two north poles repel each other, just like I didn't try to answer why do two electrons repel each other. I said they did, this is the equation, this is what we've discovered. Yeah.
So every time you use the magnet to pick something up, does it cost the energy to do that and make the magnet weaker?
I wouldn't say it makes the magnet weaker in a perfect world. Okay? Now, there might be a collision here, and as I pick it up, it may jar some of those iron atoms out of alignment. So in that sense, it would make it weaker. But forgetting that for a moment, just the fact that I bring it near and pick it up, all that tends to do then is take, as we'll see, the energy that is in the magnetic field and twist the atoms. But I get that back when I pull it away. I put work back into it. So ultimately this is just as strong as it was here, and then I pull it away. No different than if I let a heavy object fall, there's less energy in the earth stapler system. And if I pick up the staple, now energy is back into the system. Yeah, exactly the same way.
When you put the electromagnet in the bed of nails, like I noticed one nail attracted to the other. Is that because of the current going through the nails, or is it?
Well, that one was so strong, right? That I am. Remember that polarization of charges? I'm doing the same thing here. I am polarizing this atom, these atoms, not permanently, so they're not going to stay there, but they are a magnet for that moment while they're near this one. And so when I put this one here, it becomes a magnet that can then interact with another, and interact with another. But, you know, something, maybe, you know, like that.
Nails become a magnet now?
Okay. And so they are polarized. I have pushed on the electrons, not changing their direction, but I have separated them away just like I did for electricity. And they're going to go back in just a second once I do that. And so it's a polarized magnetic field.
You said the magnetic field of Earth is related to the melted core and or orbital around the sun.
Right.
But does that mean since the orbital isn't a complete circle, isn't like a perfect circle, does that mean the magnet is tilted too? Because
Now, are you mixing orbit with spin?
yeah, the spin.
Okay.
It's not like we're not spinning on a perfect
Right.
vertical axis.
Exactly. So right. So neither is the magnetic field.
But
Perfect.
then all the compasses show a different direction.
Exactly. So the compass does not really point exactly north.
That's why there's like true north and.
There's true north and magnetic north. So let me get that far here, but I hopefully, before we get to any math here, let me show you one last thing in this concept here, and that is, now that we saw what I call the first big 3 points here, this last one, that the magnetism comes from these moving charges, and I think I got that across really well, is I haven't even done anything about the field. Remember back here on number 2? How did, say, this magnet here know it was supposed to be pushed away from that magnet? And it's fields. Didn't we do the same thing for our electric charges? Didn't we do something like this? That if I had a positive charge and I put another positive charge near it, we started by saying there would be a repulsion, right? Then, as we got later on into that chapter, we said, how does the second charge know it is pushed away from the first charge? We said, because the first charge made something which we represented with arrows and the symbol E for the electric field, and we said it creates an electric field, and it's this electric field that pushes on that. Fair enough? And so I'm trying to say exactly the same thing here. How does this first magnet push on the second magnet? And so the first magnet must create around it a field. And so these moving charges that are in here create a field, a magnetic field. And to the best of my ability to illustrate it, because again, like electric fields, you can't see these with your eyes, let's take a close look at this bar magnet. Now, I'll label which side is north. In fact, I already labeled one over here, which one is north. And what did I do with the one when I put the little dot on? Ah, here it is. And so this is the north-seeking pole. Let me place that down on this overhead here. Of course, you're not going to be able to see the dot on the overhead, but I'll put my finger on it, and so this is the north. This is the south. If I take some little tiny pieces of iron, well, maybe I better not pour them out here. You'll see them here in a second. But they're really tiny pieces. We call them iron filings. We just took a piece of iron and scraped the iron, and little pieces come off here. And if I were to place them, each individual one would line up or have a force on it in the direction of the field. And so this is my attempt to give you a visual effect of what does this field look like. And so if I were to come over here and draw it, maybe I even do a different color here. I have, and let me switch it to the same direction that I put up there. So this is north and this is south. But what I have is a field that, for better or worse, is a bit more complicated looking than what we had for the simple electric field from a single point. So from a single point, the electric field was much, much simpler. And you'll see it was much easier to calculate than we're about to get into and try to calculate for the magnetic field. So the magnetic fields, as you're going to see, have a lot of analogy to electric field, but there's a couple things that are different, and they make, unfortunately, the math significantly harder. Yeah.
The electric field has a direction from high to low, positive to negative. What about the...
So glad you asked. All right, so not only am I trying to say that we have a field, in this case electric field, that creates an electrical force, here we have a magnetic field which then is going to create a magnetic force. And we should have a direction with it, right? So just like we had a direction here. What was our definition for direction here? Okay, we started with the idea of the direction of the field would be the direction that a positive charge would move. Our test positive one. Okay? Now we can't quite do the same with magnetism, because with magnetism things don't actually move, they just twist. Right? There's a positive and a negative. You know, if you put a magnet here, which is near the Earth's magnetic field, notice this did not go racing towards the North Pole or racing towards the South Pole. What did it do? It just twisted, right? And so we call that a compass today. Same thing here. These have a direction. They are defined as the direction that a compass would point. So I happen to have a compass. Yeah.
But with paper clips, it did go racing to the magnet, right?
Ah, fair enough. Fair enough. I guess what I really meant by that, let me draw a better picture. When I go north and south, and there's another magnet nearby, let's say one over here, south, then this end of the magnet would be attracted, but that end would be pushed away. So there is a twist effect. However, as you pointed out, this one is a little bit closer than that one. So as this one gets pulled and this one gets pushed, not only is there a twist, but if this is a little stronger than that, then there is a net pull. Yeah, so this, as you pointed out, if this was the paper clip, you would end up getting attracted towards there because there's a significant difference between them. In the case of the Earth, this side of my bar magnet here and this side of my bar magnet are not significantly any closer to the North Pole, so they really don't have a net force towards the magnetic North Pole, or geographic North Pole, which is, as you pointed out, a magnetic South Pole, because of that difference. Yeah, so good point. And you're right, it did. In this case, these are why I'm using little tiny pieces of iron, because this little tiny piece of iron right there would only twist. It would not get pulled in, because that little piece, the North Pole and the South Pole on there, really aren't any closer to that North Pole. And so it's maybe a hair closer, but there's enough friction on that plastic surface that they don't go in like the paper clip did. Yeah, good point. Good point. Yeah.
There's charged particles. They're not repelled or anything. They're actually pulled towards the poles of the magnet, right?
Yeah, now let me just be careful. Your first part said charged particles. Yeah. Now, do they have a magnetic field?
Yeah. Swimming charges.
Okay, so if I had charged particles that were not moving, they would have no magnetic field and they would not be affected by my magnet. Fair enough? But if I had charged particles that were moving, now because they're moving, they're also a magnet and they would be affected by my magnet. Yes. And they would get pulled, what I will soon show you. Yeah, they will get pulled and pushed once they're moving. But that was the key of the lesson so far, that they got to get moving, because you are only going to get a magnetic field if you have moving charges. Yeah.
So you say that in the in a non-magnetic iron,
Yeah.
the atoms cancel each other, cancel the neighbor out with magnetic field. How does that happen exactly? Does it because north faces north or south faces south, or?
Yeah, two fields added together in the opposite direction cancel out.
So can we make a monopole out of that?
No. No. All right, now, what I was starting to show you, oh, question, yeah.
With this experiment, they're like standing on specific paths. What happens in between?
There still is a field in between, and the same thing here with electric. We only draw a few of them to kind of illustrate, but the truth is there's a field everywhere in between.
So it's just a coincidence that
Yeah, they're nice to me, and instead of laying out just in random order, they will actually, when one twists this way and one twists that way, they'll kind of want to butt up, and they'll actually draw little lines for me. But there actually is a magnetic field between them. Yeah. And then they, like I said, it really gives a nice visual effect of the field because they'll kind of draw the shape of the lines for me. But now finally getting to your question about direction, yes, there's got to be a direction. And this compass might be a little bit too small for you guys to see, but I want to stand over here away from all my other magnets, and you can see that there's a red side, and that's the one that's pointing towards the north. If I were to hold it in my hand level and then kind of twist it so you can see the north is the red one. Now when I put it on the overhead, you're not going to be able to see red, but maybe what you would also be able to see is it has a hole in it. And so the side with the hole is the north-seeking side, and the side without a hole is the south-seeking side, because if I put this little compass right there, then what you are saying here is that compass points this direction. And so our definition of the direction of the magnetic field, now remember, for electric field, our definition was the direction that a positive would move. For our definition of the direction of the magnetic field, it is the direction a compass would point. And so the whole reason I put the compass there was to ask, which way is the compass pointing? So at this location, it's pointing that way, right? And so that would be the direction of the field. Let me move it to a different location. Let me move the compass to right there. What direction does the compass point? There, right? And we can continue this all over, like back here. Which way does the compass point? And so, as I move that little compass around, I would then get the direction of the field. And so A, we have a field. B, it has a direction. The definition of our direction will be the direction that a compass would point. Okay? You might be able to see it also, but I don't think that one's strong enough. I noticed Don brought this out, but the last time I used it, it wasn't really strong enough to see everywhere. Maybe it is. And maybe I'll refocus the plane. There we go. And there, other than a few of them look messed up, they are pointing. Oh man, there's a lot messed up. Don't even look at that. Okay, never mind. Back to there. Yeah. So some of those little compasses are fouled up. So, but back to this. The point I'm trying to get in this last little part before we start getting into the numbers is that there would be a field and there would be a direction. Now, even if I didn't put the compass on here, I bet you could have told me the direction. Because remember the one I'm holding in my hand, the red side, the one with the hole, it is a north-seeking pole. It would be attracted to what side of the magnet? South. The south. So it doesn't surprise you, I hope, that our magnetic field lines point into the South Pole. And so they come out of our North Pole. Just like in electricity, they come out of our positive charges, they go in or terminate on our south pole, just like we would have them terminate, oh, that's not a negative, negative, just like they would terminate and go inward on a negative one. Okay, so I'm not going to call those positive and negative, but I am going to say a magnetic field begin at north poles and they terminate at south poles. Yeah.
So just like the electric field needs a positive and negative to have an electric field, you need a north and a south to have a magnetic field.
I do not need a positive and a negative to make an electric field.
Oh, yeah, because
Right.
with positive you have electric field pointing out.
Yeah, that's all you need.
And with the negative, well, with the north and south,
Well,
like
if
theoretically, if you have the north pole,
then I would have something. If we could ever find something like this, then the magnetic field would look just like that.
oh, so it will have a magnetic.
And it will have a magnetic field. Sure. Sure. But I'm glad you say it like that, if we ever find it. Because as I said, there's a lot of speculation that it does exist, although there's also some very good reasons to say they don't exist. And I'm of that yes, I'm in that camp, that school, whatever word you want to, put there. Okay. So I don't think don't get me wrong, I think it's worth the effort to find it because, nobody has, the answer for sure. So we should keep experimenting and seeing if they come up. They would have some amazing advantages to our modern world of electricity and magnetism. So it'd be great, but we haven't found them, and like I said, I don't think we will. But let's keep looking, right? It's kind of like, it's highly unlikely I'm going to win the lotto, but yet I still keep playing, Somebody's got to win, right? It's just not going to be me.
You'll find something else by accident.
Right, exactly, yeah. Amazing how science works that way. All right, so now, finally, let's get into the numbers. And I went a little long, but I want to spend about the first hour giving you kind of that gut feeling, showing you how magnetic fields, like electric fields, there's a lot of things the same, and there's a few things that are different. And so, and maybe I shouldn't have erased it, because I should put that electric field back on here, because I think what will help us with the math and the understanding of the math is we also kind of review what did we do for the electric field. And so for the electric field, we did something like this. We said, okay, let's take a positive object. Let's label the electric field E and say that the direction of the field is the direction that a positive would move. Okay, we already did that. The direction of the magnetic field is the direction the compass would point. Okay. How did we define an electric field? Do you remember? Didn't we say, let's do the definition of an electric field as the amount of force that would be on 1 coulomb of charge? The force divided by how much charge you put there. And so that's why we had numbers like this. If we said the electric field was 100, what we meant by that was 100 newtons per coulomb, right? What we meant was that if you put 1 coulomb of charge there, then you would get a force of 100 newtons, right? Now, 1 coulomb was a lot of charge, so we probably never actually put 1 coulomb there. Maybe we put a microcoulomb there, but so we would have a microcoulomb times 100 to figure out the force. Fair enough? We're going to do exactly the same thing. We are going to define our magnetic field based on how much force it puts on another charge. Let me draw the picture here. And so, if I put a magnet up here, and maybe I'll draw just a little bit of the field. Okay, there's the field. There would be the direction. I will label it with the symbol B. So there's kind of our first piece of math. What symbol do we use? We use the symbol B for magnetic field. How would you define it? Well, what if I put a charge right here?
But attachment of the charge, it doesn't move.
Ah, you see the difference. Good. Because my first reaction is to say, let's define the magnetic field as how much force is on that charge, just like we did for the electric field. But the problem with that is what? If it's not moving, there's no force. What if it is moving?
Then there probably is.
And what if it's moving slow compared to fast? All right, so here's where our magnetism gets a little bit harder, and I should add better for technology because there's more options to change and to play with. Our force. Oh yeah, there's an earthquake drill right now.
Someone's on the monopole.
Just go on.
Can you? Do you guys want to get under your desk? No. But if it was a real earthquake, you'd get under your desk, right? No, don't go outside. A lot of people get hurt, which I guess is the whole point of this drill, so we could have a discussion. Actually, they wanted you to get under the desk, but I understand you're not going to want to get under the desk. It's not going to be comfortable. But if there really was an earthquake, I don't think you would mind being uncomfortable under the desk. So in a real earthquake, get under the desk. But no, they don't run outside. A lot of people, that's where things on the edge fall off, and most people are hurt running outside in an earthquake. Yeah. Yeah, but they wouldn't be able to flap back and forth because your body would be under there. So they'd be hitting you, if that's what you mean. But again, being crowded underneath was probably better than the alternative. So you'd probably put up with it. Yeah. So I know it won't be easy to get under there, but if it's an earthquake, you'll probably get under there.
Where would you go?
Oh yeah, that's the whole point. What would I do? I fit under there. There we go. I can fit under this one. But I gotta admit, I've been through enough earthquakes that unless it's a 6, I'm probably not moving. But if it's a 6, I'm moving. And if it's a 4, I don't even want to hear it on the news. Tired of hearing, oh, there was an earthquake. Oh, really? 3.7? Yeah. And there was one tomorrow at 3.7 too, I'm sure, you know. So that's why I didn't feel it, but 3.7? If you happen to be laying down and you're fairly close,
You're not moving at all.
yeah, you can feel a 4.
Probably just hear the windows.
But I was living near Northridge during that Northridge quake of the 6.7. And believe me, when buildings are falling down next to you, you have no concern about getting in there. And those were the kind of earthquakes that I was just like, you thought the building would fall. I mean, I don't know how the building I was in did not fall. I mean, it shook like crazy. Anything that was on the wall came off. Anything that was on this desk was all over the place. So you'll know, huh?
How much was
The Northridge was 6.7, I think was the final reading on it. Huge, yeah, huge shaking. Broke everything. I mean, and then once the earthquake's over, now some of the worst things can happen because all the gas lines are leaking. I mean, the building was shaking so bad, gas was pouring out in the room. So now it changed from, okay, let's stop being under the desk and let's get out of here before this room fills with gas and we all blow up and burn. So then it was...
Earthquake valve.
And then the people, unfortunately, who did get burnt, and yeah, and that's why the valves are there, and things fell on them. The hospital that was down the street fell down. That was some of the worst, because the people who really needed the hospital didn't have a hospital. And then they needed to get to a hospital, but you couldn't get to the hospital because all the roads were blocked because of all the debris that was on the ground. So unfortunately, there was a lot of additional casualties that would have been fine had they been able to get to a hospital in time, but bummer. Oh. I do remember this. In fact, I still have one in my office. It's pretty cool. It was Northridge, and there's a bottling company there. It's one of the beer companies. I think it's Miller. No, that's Irvine. No, it's not Budweiser. Is it an Anheuser-Busch? I think it's an Anheuser-Busch that's near Northridge there. Oh, now I can't remember which one it was. But anyways, we were like 2 days without water, and it was getting kind of desperate of like, ooh, you know, what do we have no water. I'm getting kind of thirsty here. You know, I was thinking, maybe it's time to take a hike, get on some hiking boots. We're going to go about 20 miles. Maybe Glendale has some water here. Let's hit the road here, because you couldn't drive. You couldn't go anywhere. But the bottling company stopped bottling beer and started bottling water. So instead, every day we'd get up and go for a little trek, a couple miles, and get some bottles of water and head on back. And so that was kind of our safety valve. So anyways, to this day, I kept one because it's pretty nice. It's got a beer bottle with the label, but it's got water in it. Yeah. And it just looks funny. Yeah. And so I kept it as my souvenir. Oh, anyways, all right, we better get back to this. All right. So the challenge we were talking about was right here, that the magnetic field can't be as easily as defined as just force divided by charge. It also needs to include speed. And so I'm going to put a V down here, and here's what we mean. If this charge, Q, is moving with this speed V and has a certain force F, that's the definition of our magnetic field. So the magnetic field is 1 Newton of force when you put 1 Coulomb of charge traveling at 1 meter per second. Make sense? That would be a unit of 1 magnetic field.
Couldn't it just have a rotational speed?
It could. But then we can, that would just make it harder to think about a definition. So let's define it based on a translational speed. And then if it has a rotational speed, then we can calculate its field based on taking a rotating object, breaking it into an integral of rings, and adding it up. So we'll do that soon. We will do that. Don't get me wrong. Yeah. So we'll do that. But we'll define it as simply a translational motion. Yeah.
Wait, according to the math, if the particle is not moving, just means that the field is...
No. According to the math, if the particle is not moving, 0, then there's no force, 0.
Oh, okay.
And then you have some kind of field. You have 0 over 0. It's not a good way to calculate the field, but if you take the limit, you can get it.
So according to this, the higher your speed is, the lower the magnetic field will be.
For the same force. I think what you're doing is rearranging this equation. Let's do that. If I rearrange this equation, the force on it then is a combination of how much charge do you have, how fast are you going, and how strong is the field. So the faster it goes, the stronger the force for a given field.
Also, the force changes.
Exactly. So the force, and here's what makes magnetism both fun and complicated to calculate, is that unlike the electric field, where the amount of force depended only upon how much charge and the field, the amount of force you get in magnetism depends on how fast, as well as how much charge and how strong the field. And, I haven't got there yet.
Acceleration.
It gets a little more complicated. And I haven't got there quite yet. But what I want to do before I get here, let me backtrack to this. Because again, I want you to see the definition of the magnetic field. So, the magnetic field would be in what units? Newtons per Coulomb per meter each second. A Coulomb per second would be a what? An amp. Which doesn't surprise you. I hope that amp shows in there, because wouldn't the field come from moving charges, and moving charges current? Amp, sorry. Amp meters, thank you. And like we've done so many times in the past, let's give it a name, its own name, in honor of the great scientist working in the field. And I heard somebody say it already. What do we use? Tesla. Okay? And so this is a Tesla. It's Tesla. Okay? And so our abbreviation will be capital T. Okay? Tesla. And I will point out that 1 Tesla is actually a very, very strong field. So this is the equivalent of 10,000 Gausses. UASS? 10,000 Gauss? 10,000 capital G. And so we have 10,000. No, it must be A. AU. Boy, I can't get my letters straight today. AUA. Yeah. All right.
I think you wrote it. You said it, and then you wrote it back.
Oh, did I? Okay. All right. So, although I haven't gotten very far into the math quite yet, I'm hoping you see this important step, that the magnetic field is based upon not only how much force, not only how much charge, but how much speed that is. Because the strength of the magnetic field is connected to the movement of those charges. Not just the charge, but how fast they are moving. That's the fundamental idea. Yeah?
The Newton per meter is for pressure, right?
Newton per square meter is pressure.
Is it also the amount of charges? The number of charges?
Okay, fair enough. And so at this point, this, what I would say, would be the movement. Maybe, okay, so I guess I answer it this way. The field, remember, is made by this magnet. It's measured by the movement of this one charge. So there's only one charge moving in the field that I'm using to measure the strength of the field. But the field is created by the movement of many charges in here. Okay? And so maybe to give you guys a little heads up of these next 2 chapters, this chapter, we will focus on the amount of force on the charge coming from this magnet. We won't try to calculate how the field, we won't calculate the strength of the field from the movement of all these charges until next chapter. And so one step at a time. And so our problems are going to be more like you were asking here. We will be asking, what is the force on this charge? The force on this charge is based upon how much charge does it have, how fast is it moving, which notice 0 speed means 0 force, and the field that it is in. Now the field comes from this magnet, which comes from moving charges in that magnet. So we won't calculate we won't have the ability to calculate the field from the moving charges till next chapter. And so we'll just say, this magnet gives you a field of a half a Tesla, and you have an electron moving at 3 meters per second. What is the force on that electron? And then if we know the force, we know the acceleration, and we know all kinds of other things about it. But for one step at a time, let me make it clear that you're going to be given the magnetic field. You're not going to be asked to calculate it till next chapter. Yeah.
So this formula for the force, is it the force from the whole magnet as a unit, or each pole separate?
Oh, okay. This would be the force on that charge. From the entire magnet. Right. So by Newton's third law, that would be the total force on the magnet, the whole magnet. Now, that force may come more from this area of the magnet than that one, but it's the whole magnet.
Can we calculate which part puts more force on it?
No, we're not going to get quite that much detail. Yeah. Now, here's what even gets one step harder. It's not just how fast it's moving, it's also what direction does it move. In other words, if this charge was moving this way as opposed to this way, you don't get the same amount of force.
Oh. No way. Would it be the zero?
So, if I can illustrate, I will try it with this guy here. Move this out of the way. But I have set up here a power supply and a little switch that should give me a lot of current, and I am getting no current. Why am I getting no current? Uh-oh. I will use this guy then. I don't think we're going to quite get to this one today anyways, but let me put this here. And here is a 12-volt battery that can put out a lot of current. Let me grab a couple of wires from this guy then. And if I put a wire here, and then here, and then back to here, oh, they don't have any meters on here, so I'm not sure if I'm getting current, but I bet I am. But if you watch what I have, this is the positive side. The current should go through here, through this switch, so when I tap it, it should go through here, through this little metal piece that's kind of balanced in the air. And the reason it's balanced there is so that if I put, and here's a big magnet, and I put this magnet right there, that big magnet has, and do they label which side's north? So the red side's north here. I have a north pole and I have a south pole. And so as we started to draw here, there would be a magnetic field from north to south. If I tap that switch, don't I have electrons moving? And so what we were saying here is there will be a force on those moving charges based on their charge, their speed, and their magnetic field. And so right now, do I have any electrons in this magnetic field? Okay. They are probably doing something like this. If I kind of hold it this way, there's probably a bunch going out towards you and an equal amount going that way. And so I would say the net effect is zero. And sure enough, there's no force. What if I tap the switch? Tap it. And I guess that's what I get for going over to this bigger current source. But what I want you to see is that yes, there is a force. And that force bases on, is there a speed? Is there a movement? And sure enough, when there is a movement, when there is current. Now, which way is the force, by the way? Isn't it down? Now, this is important in terms of our math and our physics understanding. Which way is the magnetic field? Okay. As I stand here, it's to my right. I guess it's to your left, right? Or correct? Left? Which way is the movement of the electrons? Yeah, the electrons look like they're coming towards me. So in this picture, I would say the electrons are moving that way. And which way is the force?
It's a right angle as well.
And it becomes very three-dimensional and a little harder to picture, and even harder still to calculate. What I'm trying to say is, first of all, the easy one. Is there a force? Yes. But what direction is that force? And the direction of that force is perpendicular to the direction they move. And it's perpendicular to the magnetic field.
So it's perpendicular to the plane they do make.
Yes. What do you think would happen if I turn the magnet around?
If you were to break the force of the electromagnetic field in confidence and the direction to make the cross product.
Oh, good. I'm glad you said that. Because they're at right angles, and fortunately, I know cross products. That's what cross products were all about. That's why we did them for torque. That's why we're going to do them here. They're going to make our equations straightforward.
Is there like a left-hand rule for this?
So if I do this, it pushes it up. And as long as I'm here, the whole reason this wire was here to begin with was to really show you the same thing, but to show it without, whoops, I don't want that, without that thing hanging around, so that what I could do is place the wire, say, in the magnet, tap the switch, and it would have a force on it. And the force, in this case, would be up. And so my picture would change. So that I have a magnetic field this way now. I have a velocity that's into the board. And as you are seeing, I am getting a force up there. Okay? Yeah.
I just noticed, as the wire left the magnet, the horseshoe magnet thing, it just curved towards you. Will it go the other way around if you put the magnet around?
Yeah. If I turn the magnet around, it'll push it down, right? Which it's already down, so it's kind of boring, but it does push it. Whoops, did I mess up? Oh, I think I changed the direction of the wire. Which way are the electrons? Okay, this way. Hopefully, let me get it. Yeah, see now it just pushes it down. What if I do what the other way? Oh, yeah, well, okay. Like that? Yeah, so now it's going to push it up.
What if your initial position was above the...
And so, well, there would still be a force up.
If the
It would still be up.
that way and electric field
Okay.
that way.
So, in the little time we have left, let me make sure I get to this main conclusion here. You guys pointed it out already here, that there would be a force. The force is based upon these three products, but it's also based upon the angle. Fortunately, we learned things called cross products. We could write this in a more advanced form, and we will. We will write it as we learned in, what do we do? Cross products. Well, when we did torque, which was what? Like chapter 10, yeah, in 121. And so we have the mathematical skill, if you will, to realize that the force on that charge in a magnetic field depends on not only the charge, not only the velocity, not only the magnetic field, but the angle between them, and the direction is perpendicular to all of that. In other words, what this equation means is two parts. There is a magnitude of the force, QVB sine theta. You might want to write this as QV perpendicular B, meaning, back to the definition that I kind of erased, and I said there was one more piece to this. The magnetic field is not just how much velocity does it have, but the only part that's relevant is how much velocity is perpendicular. And the cross products do that for us. And so you're going to be fortunate that you can put it into the equation, and the cross product takes care of the components for you. And so here is what I'm trying to say, is that the force depends on four factors: the charge, the velocity, the magnetic field, and the angle. You might be able to see it here if I go back to yeah, now I should be very clear that I'm just trying to, illustrate it. I'm not calculating it. But yeah, that would be the force on just one charge. And this wire that I'm hooking up has many charges. And so the total force is the sum of all of those. But if I come back to this setup here, and this power supply might be a little too much for it. But I'm hoping maybe we can still see it. When I line it up this way, and I'll turn it this way so you guys can see it a little bit better. But when I line it up this way, I get a lot of force. In fact, probably too much for me to kind of see what you want to see. But I'm going to try it anyways. See how that's a lot of force? What if I were to put the magnet this way? Right, now what direction is the field and what direction is the flow of charges? They're the same. So what do you get with this cross product? Yeah, so in a perfect world you'd get 0. I can't actually make it go right through the center, so I'm slightly above it. But I should get a force that is hopefully a lot less. I mean, it does twist it a little bit. If I were to twist it just a little more, I would probably get a little more force. If I twist it a lot, I'd get a lot of force. And so my point here is that the force on these moving charges in a magnetic field depend on how much of the velocity is perpendicular to the field. And the second part of this is the direction. What direction is that force? And as you guys already saw in this drawing, the force is perpendicular to the plane that is made up by the magnetic field and the velocity vector. And so that's where our little cross product thing came into play. And so if I apply it to this scenario, let's see what I get. Yeah.
Can you show us the right-hand rule for these?
Yeah. So, did they came backwards? You're missing one thing. All right. So let's go through this. Let's set this up and look at this equation. When you go to do a cross product, like you learned for torque, is you put your fingers in the direction of the first vector, and you close them towards the second vector, and your thumb gives you the direction of the cross product, right? So let's try that. V cross B. All right? So I will take my right hand. I will start with this one since we did it first. I will put my fingers in the direction of V. Into the board. I will close my hand towards the second vector, B. My thumb, now hear this carefully, gives me the direction of the cross product. Because I got one more step to do. What's the next step? I now need to multiply by the charge. Now, are these positive charges or negative charges? Negative. So when I multiply by a negative, it changes the direction of the cross product, right? So V cross B is up times a negative number is down. So which way did they go? Down. And it was probably the negative you were overlooking, right? So again, maybe that's why you were asking earlier, is there a left-hand rule? So we try it again. Now, you've got your left hand. Oh. Well, okay, so if you want to do electrons with your left hands and protons with your right hands, fine. But I think it's best, I think it's best said, this right-hand rule gives you the direction of the cross product. Then you multiply by the charge, and the charge may be a positive or a negative number depending on what we're working with. And in my illustration, I'm working with negative objects, so I got to multiply by a negative. Well, let's do the right-hand rule here too. If I take my right hand and put it in the direction of the velocity, which is into the board, but in this case I need to kind of rotate my hand so I can close my fingers towards the second vector, which is the magnetic field. V cross B is down. That's the direction of the cross product. Then multiply by what the charge was moving, which are negative guys, so the force would be up. And so sure enough, there's our direction of our cross product. All right? So let me sure I make this very, very clear. Notice, because we're going to do some clever things here at the second half of this chapter tomorrow or Thursday, where Tuesday, where the force depends on all four options. How much charge do you have? How much field do you have? I think those are the obvious two, because those were the same two for electric. But how fast are they going and at what angle makes it a much more interesting problem. Because, watch this. What if I, as you pointed out, said this? That you see these charges, these are not individual charges that are moving. In fact, it's really hard to get just individual charges to move. I mean, I can do my best. That's kind of what this setup is for. This setup is a high voltage energy source here that will send electrons through this tube to the other side. So this charge, or this side, will be charged up highly negative, and this side highly positive, which is why they go from negative to positive. I mean, there's so much charge on here. I think this is like 25,000 volts, that when I put them on here, they're just going to leak electrons off. There's so many electrons, they're just shooting each other off. Now, unfortunately, you can't see electrons with your eyes. So, in addition to having this tube, which by the way, the tube is evacuated because again, unfortunately, if this was done in the air, they would just bounce into air molecules and they wouldn't go very far. So I put this in an evacuated tube. I'm going to charge this up to 25,000 volts. Electrons are going to come racing across. Again, there's nothing I could see if that's all that was there. You will probably notice there's a screen here. That screen has inside of it phosphorus. And when electrons hit phosphorus, they give off green light. And that's an interesting discussion in itself, why they give off light and why it's green. But let me skip on that to just say, if I turn this on, do you see some green light? And what's happening is those electrons are going across. Again, you can't really see the individual electrons, but you can see them when they hit the screen. And so this white screen is actually bowed out towards you so that some of them hit on this part of the screen right away, some of them go all the way across and hit on that part. And so you see this green strip where these electrons are going across. So what do you think would happen if I brought a magnet near it?
It would bend.
All right, and so I will hopefully get a deflection up or down, sideways to my magnetic field. Well, bottom up. And so, however I want to stand here, I won't have time to get too much into direction, because I want to show you one last one. Same idea, and again, I can't really get individual electrons, but I do have let me turn this off before I forget and electrocute myself. All right, one of these old guys, which you may or may not recognize. But here is an old black and white TV that is just on. There's no channel to it. And yes, it is ancient. In fact, I got this from my grandma. And one Thanksgiving, my oldest son, he was 5 then, was too antsy to sit at the table and talk anymore, as us old people were kind of just chatting after the dinner. And I said, well, go watch TV. And he said, well, Grandma doesn't have a TV. I'm like, oh, shoot. Yeah, she does. She's got an old one in the closet. Go into her bedroom, pull it out, plug it in. So he's gone for a little bit. He comes back. Dad, TV's broken. No. And he wanted to watch some cartoon. And he kept coming. No. Finally, I got up. I go, okay, let's see what's broken about it. So I get in, and the cartoon, I think it was Mickey Mouse. He's running around. Oh, what's wrong with it? He's all, well, look at it, Dad. Well, I'm looking. I don't see what's broken. It took me about 30 seconds. What he meant was, it's not in color. There's no color, Dad. The TV is broken. So he was introduced to a black and white TV. All right, but what I wanted you to see was that the way these older TVs, not obviously the TVs are different now, but they would send electrons from the back forward and hit the screen. That's why they have a size to them. But I'm going to use it as, don't I have moving charges? Aren't moving charges affected by the magnetic field? So what happens if I put a magnet near it? All right. It should take these electrons that are racing up, and I don't know if you guys can all see that over there, but as it goes racing up, they get deflected. And if you looked real carefully, and it's hard to see because this big magnet kind of blocks your view, where are the electrons not deflected? Can you see right behind here? There still is electrons hitting the screen. Because this magnetic field goes like this. So the electrons that are going this way are going parallel to the field. What force is on those electrons when they are parallel to the field? Zero. And so those electrons are not pushed at all. The ones on the side have a perpendicular component and they are pushed. But these are not. They go straight in there. All right, well, more on this next time.